right, day 4 of Exponents and Logarithms, and today we're going to look at graphing logarithmic functions. But the first thing we're going to do is we're going to look at this function here. So y equals b to the x. And the first thing that I will ask you to do is to find the inverse of that function. And so finding the inverse, the first thing we've got to do is switch x and y. So I can rewrite this as x is equal to b to the y. And then we need to re-isolate y. And so how do we get our variable out of the exponent? Well, we convert it to a logarithm. So the base of the exponential becomes the base of the logarithm. So this is going to become log base b of x is equal to y. And so we have re-isolated y, and what we see is that a logarithm is the inverse of an exponential. So let's try some of these. So find the inverse of each of the following. Okay, so switch x and y, isolate the exponential or the logarithm, and then change to a logarithm or an exponential. Okay, so here we go. First one, I'm going to rewrite this as x is equal to 5 to the y plus 3 minus 1. And we're going to look to isolate the exponential here. So I'm going to take that negative 1, move it to the other side. We get x plus 1 is equal to 5 to the y plus 3. And from here, we will convert this exponential to a logarithm. So the base of the exponential becomes the base of the logarithm. So we're going to get log base 5 of our solution, which is x plus 1. That becomes the argument of our logarithm, is equal to the exponent, which in this case is y plus 3. And the last thing we need to do is get rid of that 3. We'll move it to the other side. We get that y is equal to log base 5 of x plus 1 minus 3. Okay, next one. So this is a logarithm, and we want to find the inverse of it. So we're going to start by switching x and y. So we get x is equal to log base 8 of y plus 1 plus 3. Okay, we will isolate the logarithm, so I'm going to move that 3 to the other side. So we get x minus 3 is equal to log base 8 of y plus 1. And now let's convert the logarithm to an exponential. So the base 8 raised to the power of the solution, x minus 3, is equal to the argument, which is y plus 1. And then we'll just move that 1 to the other side. So we get y is equal to 8 to the power of x minus 3 minus 1. And there we go. Okay, next, so make a table of values and sketch a graph of y equals log base 2 of x. Okay, so this is one of our basic logarithmic functions, and we want to know, what does the graph of it look like? Okay, well, the easiest thing for us to do would be to use the exponential form of the logarithm. So I'm just going to make a note here. So let's use, and I'll explain that in just a minute. So use exponential form to, and I'll say to create a table of values. Okay, so what do I mean by that? Well, y equals log base 2 of x is the same thing as 2 to the y, oops, I'll do this in blue, is the same thing as 2 to the y is equal to x. And I think it's much easier to create a table of values with 2 to the y equals x than it is y equals log base 2 of x. Okay, so I'm going to create my table of values here. And we're so used to selecting values of x that are near the point of origin, and you can still do that, but you'll end up working backwards, and in this case it'll be much easier for us to select values for y. So I'm going to select -3, -2, -1, 0, 1, 2, and 3. We're plugging those into the equation now for y. We're solving for x. Okay, so let's just start here. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 squared is 4. 2 cubed is 8. And then just be wary of our negative exponents. So 2 to the power of -1, the negative exponent tells us to reciprocate the base. 2's reciprocal is 1 over 2. And then the exponent becomes positive, so this just becomes 1/2. This is going to be 1 over 4 and 1 over 8. Okay, so we've got a number of different points there that we can plot. You can plot those points, and then we're going to connect the dots. Okay, so we should end up with something like that. And so let's talk about some of the properties of this function. So x-intercept, we have an x-intercept at 1. We do not have a y-intercept, and but what we would notice is that there is a vertical asymptote, and it's got the equation x equals 0, which is our y-axis. Domain x is greater than 0, and our range y is an element of the set of real numbers. Okay, so some alarm bells might be going off here. This looks awfully similar to an exponential function, and you're right. They share many of the same properties, but in reverse. And if you are starting to put all this together, we looked at exponential functions and logarithmic functions as being inverses of one another, and inverses when we switch x and y. So you'll see that the domain of an exponential function becomes the range of a logarithmic function, and vice versa. Okay, so let's talk about some generalities here. So if we're looking at some function log base a of x, okay, and a is greater than 1, so our base is greater than 1, our function is going to look something like this. And the example that we just did had a base of 2. So it's going to have an x-intercept of 1, and that is when we raise something to the power of 0, our outcome becomes 1. So in this case, our y-coordinate is 0, our x-coordinate is 1. And let's just use log base 2 of x, the example that we just did. So if our y-coordinate is, say, -1, then our x-coordinate is going to be 1/2. If our y-coordinate was 1, our x-coordinate is 2. And I'll just fill in the gaps a little bit here. but this is the basic shape of a logarithmic function with a base greater than 1. Okay, something like that. Okay, but what happens in this scenario? So a, our base, is between 0 and 1. Okay, well, let's come up with an example for that. Let's say our function is this. Y equals log base 1/2 of x. Okay, so now our base lies between 0 and 1. Let's convert this logarithm to an exponential. So I'm going to rewrite this as 1/2 to the power of y is equal to x. And from here, we can create a table of values so we get a sense as to what this looks like. Okay, so again, I'm going to choose values of y here. And I'm going to use -3, -2, -1, 0, 1, 2, and 3. So remember those negative exponents, we reciprocate the base. So this is going to become 2 to the power of +3 is 8. We get 4, 2, and 1. And then this is 1/2, 1/4, 1/8. So let's plot some of these points. So x coordinate of 8, y coordinate of -3, x coordinate of 4, y coordinate of -2, 2 and -1, 1 and 0, 1/2 and 1. Okay. Connect the dots here. And there's the graph of log base 1/2 of x. Okay, well, let's make some more direct comparisons then between exponential functions and logarithmic functions. Okay, so a base exponential function, y equals a to the x. Okay, so if a is greater than 1, so we talked about some terminology for this, we would say that this is an increasing exponential function. And the graph is going to look something like that. See a lot of these on the news lately. Okay, so we'll say this is an increasing exponential function. The domain is all real numbers. The range, values of y that are greater than 0. It's got a horizontal asymptote at y is equal to 0. And it's got no x-intercepts because of that horizontal asymptote there. Okay, if our base is between 0 and 1, okay, so our base is less than 1 but greater than 0, here's what it's going to look like graphically. Something like that. And we call this a decreasing exponential function. And a lot of the properties stay the same. So the domain is still all real numbers. The range is the same, and we still have a horizontal asymptote at y equals 0. Okay, but how about a logarithmic function? Okay, so we've got y equals log base a of x. Well, let's look at what happens if our base a is greater than 1. Okay, so we've looked at an example of that, and it looks something like this. Okay, well again, we would call this an increasing logarithmic function. So as x increases, the value of the function increases as well. Now, some differences here, or opposites. The domain of this, x is greater than 0. Okay, compare that to the range of an exponential function. Okay, so we're switching x and y. These functions are inverses of one another. Okay, range, y is an element of the set of real numbers. Okay, this one doesn't have a y-intercept because it has a vertical asymptote at x equals 0. Okay, and let's look at a logarithmic function with a base between 0 and 1. Okay, so a is less than 1, but greater than 0. We just looked at an example of this. It's going to look something like that. Okay, vertical asymptote on the y-axis. Properties here stay the same. Domain, x is greater than 0. Range is all real numbers. And let's just label this. So this is an increasing logarithmic function when the base is greater than 1. And then this is a decreasing logarithmic function. Okay, so moving on. So this is our skeleton transformed logarithmic function. And a lot of this is, all of it should be familiar to you. We can transform any function we want to. If we multiply the logarithm by some value a, it's going to expand or compress the graph vertically. It's going to flip it over the x-axis. If we multiply x by some value b, it's going to expand or compress horizontally or flip over the y. If we add or subtract something to x, it's going to translate the graph left and right. And if we add some value q to the function, it's going to translate the graph up and down. Okay, so if we're given some base function like this, y equals log base 2 of x, can we identify the transformations that have taken place? Okay, so we've got log base 2 of x minus 3 minus 4. Okay, so we've got a p-value here of 3, a q-value of negative 4. So this is shifting the graph 3 units to the right. And 4 units down. Okay, the next part to this is determine the domain. So I'm just going to give you a quick sketch again. Oops, I'll do this in blue. Okay, so log base 2 of x, just a very rough sketch, is going to look something like this. Now we've got a vertical asymptote on the y-axis. So the equation of that asymptote is x equals 0. The domain of that base function, log base 2 of x, is values of x that are greater than 0. Now we've shifted this graph 3 units to the right. That's going to impact our domain. So we will say values of x that are greater than 3. Okay. So next one here, what are our transformations? Okay, well we've got a b value of 2, so that is going to be horizontal compression by a factor of 1/2. We've got a shift of 3 units to the left and a shift of 1 unit down. Okay, now what's happened to our domain? Horizontal compression by a factor of 1/2, that's not going to impact our domain. The shift of 1 unit down, that's not impacting our domain, but shifting 3 to the left will. So our domain is going to be x values that are greater than -3. Okay. Next one. Now we're multiplying the logarithm by 2. So we're going to have vertical expansion by a factor of 2. Oops. And we're going to have a shift of 1 unit to the left and 2 units up. Okay, it is that translation of 1 unit to the left that impacts our domain. Our domain, x has got to be greater than -1. Okay, and this next one, I just want to be careful with this. This is not in factored form. And so hopefully you remember back to our transformations unit, we must be looking at a function in factored form so that we can do our transformations in the order they appear, from left to right. Okay, so my first step here is I'm just going to rewrite this in factored form. So we get y is equal to log base 2 of, and I'm just factoring out a 1/2, which leaves us with x minus 4, and then minus 2. Okay, so that's a b value of 1/2, which is going to represent horizontal expansion by a factor of 2. So HE, horizontal expansion by a factor of 2, and then a shift of 4 units to the right and 2 units down. Okay, how does our domain change? Well, we're shifting 4 units to the right. That's all that matters here. So our domain is values of x that are greater than 4. Okay, moving on. Determine the domain of this. Okay, so we've got log base x minus 1 of x plus 3. Okay, so we've got to look at some of our restrictions here. So let's look at this in 2 parts. We're going to look at the domain of the base to begin. Domain of base. Now, what were some of the restrictions on our base? Okay, well, the base cannot be negative, and it also can't be 1. Okay, so I'm going to make a little inequality here. So I'm going to say that x minus 1, which is our base, it can't be negative. So our inequality is going to be x minus 1 has to be greater than 0. Okay, but I'm just going to leave a note for myself in brackets. I'll do this in red. So base also cannot be 1. Okay, so we'll solve the inequality, and we're going to get values of x that are greater than 1. Okay. Now, what value of x, if we were to input into our function 4x, is going to provide us with a base of 1? Well, 2. input 2 for x, we get 2 minus 1 is 1, and we know we can't have a base of 1, so the domain of the base is going to be values of x that are greater than 1 with the exception of 2. Okay, so I'll just put a little box around this so that we're not getting confused. So this is the domain of the base. We also have to look at the domain of the argument. And then finally, we're going to look at what do the two have in common? What values of x are shared by both? Okay, so the domain of the argument. Okay, so the restrictions on our argument, it's not so much that they are restrictions, it's that if we're following the restrictions on the base, these are the arguments that would be impossible to come up with. And so what would happen is it would be impossible to come up with a negative argument. Okay, so we can create an inequality here. We can say x plus 3 has to be positive, so it has to be greater than 0. And so we would say that x has to be greater than negative 3. Okay, so this is the domain of the argument. Now, combined, what do the two have in common? Well, it's the domain of the base. So the combined domain here is that x has to be greater than 1, but not 2. Okay, I'll double box this. So these values of x satisfy both parts of this equation. All right, so the last thing here, we're going to graph some transformed versions of logarithms. Okay, so how to graph log functions. Determine the parent function. Okay, so what we mean by that is log base 2 of x plus 3 minus 4 is a transformed version of what? Well, it's a transformed version of log base 2 of x. Okay, so determine and plot the key points of the parent function. Okay, so again, I can convert this to an exponential to help with that process. I'm going to rewrite this as 2 to the y is equal to x. And we can create a quick little table of values here, x and y. And again, I'm selecting values of y here. So negative 2, negative 1, 0, 1, and 2. And we'll plot those points. Okay, so there is our parent function log base 2 of x. Now the whole idea here is we do not need to create another table of values. We need to apply transformations to our base function. Okay, so what's happening here? Well, we've got a shift of 3 units to the left, and we've got a shift of 4 units down. Okay, so let's just take each of those significant points and we'll go 3 to the left. So 1, 2, 3, and down 1, 2, 3, 4, and plot a point. Okay, 1, 2, 3 to the left, 1, 2, 3, 4 down, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4. think I've got enough there. We'll connect those dots. And one of the things that you start to see is, okay, so the parent function has a vertical asymptote at x equals 0. This has been transformed 3 to the left, so that vertical asymptote should go to x equals -3. And that's kind of a landmark for you when you're graphing the transformed function. Okay, so in red, we've got log base 2 of x plus 3 minus 4. Okay, and last one here. So our parent function is y equals log base 1/2. Y equals log base 1/2 of x. And again, we can convert that to an exponential. So this is going to be 1/2 to the power of y is equal to x. And we can just do a quick table of values. Again, selecting values for y. Okay, so -2 is our exponent. Reciprocate the base, it becomes +2. Squared is 4. 2, 1, 1/2, and 1/4. Connect these dots. Okay, so there's our parent function, log base 1/2 of x. And so what's happened here? Well, we've got an a value of 2, so vertical expansion by a factor of 2. And then a shift of 1 unit left and 2 units up. Okay, so vertically expanding by a factor of 2, you're doubling the y coordinate. -3 goes to -6. 1 to the left, 2 up. -2 goes to -4. 1 left, 2 up. -1 goes to -2. 1 left, 2 up. 0 stays at 0. 1 left and 2 up. 1 goes to 2. 1 left and 2 up. 2 goes to 4, 1 left and 2 up, and we should end up with something like this. And that vertical asymptote that was at x equals 0 is now at x equals -1 because we've translated 1 unit to the left. Okay, and that is it for today. Homework down below. Until next time.